Hi everyone, and welcome to August A3D3 seminar. It is my great pleasure to introduce our speaker today, who's Dr. Benedikt Maier. Benedikt is an Eric and Wendy Schmidt AI in Science postdoctoral fellow at Imperial College London, where he leads the epigraphy network to advance deep learning solutions for real-time edge computing in particle physics experiments at the LHC. He specializes in searches for new physics and dark matter, particularly working on machine learning methods for both data analysis and large-scale computing. He's the winner of the CMS Young Researcher Prize, which highlighted his sustained contributions at the intersection of high-energy physics and artificial intelligence. And so a great speaker, very much in line with what we do in A3D3. So I'm very pleased that Benedikt's able to talk to us today on machine learning anomalies in high-energy collisions. Benedikt.
Yeah, thank you very much, Matthew, for the great opportunity to give this seminar today. Even though it's vacation time, I'm at a conference right now this week, so it's a great. I'm maximizing my time usage and even in the lunch break, giving this nice seminar. So thank you very much for attending. And indeed, I'll be talking about how we learn anomalies in our data and what we can infer from that in terms of existence of exciting new phenomena that might shed light on some of the biggest mysteries in the universe. So let me begin slowly with an anecdote that brings us back now 7 years almost to September 6 in 2018, where CMS recorded the following event in the detector. You can see here the innermost tracker that records charged particles. You see here some calorimeter energy depositions in our detector. But most strikingly, you see here what is called a multi-jet signature. So you see these collimated bundles of highly energetic particles. Each line is basically a particle that are collimated and fly into various directions in the detector. In this case, we observe 3 of those so-called jets. And now the interesting thing about it to begin with is that if we assume that some of these jets may come from a new particle that has been produced at the collision and that wasn't stable, but it decayed into these jets, and we assume that these jets, for instance, came from a common origin, from a common new particle, then we can infer the mass of this particle at the origin, and we conclude by measuring the energies of the jets and the momenta of the particles in the jet, that this common origin particle would have had to have a mass of roughly 4.5 TeV. And this is interesting because at these energy scales, standard model processes, known processes from our super well-established theory, the standard model of particle physics, are already quite suppressed. So this is kind of a already very rare event from standard model theory point of view, which is why this is interesting for us, right? It is also interesting for us from a very different standpoint that I will come to in a few slides. So, but to set the scene, and I already alluded to it, there are really many open questions in cosmology and particle physics. Some are experiment-driven. Most famously, what's the nature of dark matter and dark energy that make up so much of the mass energy contribution in our universe? Where does this apparent matter-antimatter symmetry come from? Some are theory-driven, like what are the hierarchy problems? Where do they come from? These problems that we're confronted with, that, for instance, gravity is so weak compared to other forces that there is this apparent insane level of fine-tuning with respect to the Higgs boson mass, for instance, would have to be normally, from first considerations, orders of magnitude heavier than it actually is. So maybe there's another particle canceling the mass contributions to the Higgs boson and brings it down to something where we can see it at the LHC. Why are there exactly 3 generations of fermions? All these are big open questions, and that led us to believe that there is some new force, some new particle around that hopefully answers most of these questions, or as many of these questions as possible. And we really hope we can shed some light on this new, whatever it is, at the LHC, and that's why we're probing it at the LHC. So this is the outline of my talk. I will first talk about how exactly we do machine learning for anomalies at the LHC and what I mean by this. Then I will talk about an outlook into the next 10 years. And finally, I'll talk about how we, maybe the next 100 years, I didn't want to call it like this, but certainly what we can do by tapping the quantum realm in intermediate term quantum computing strategies. So first, I already told you we're probing a dark sector, a new potential interaction at the LHC. We're doing this with the CMS detector, me specifically, which is really built like an onion. It has several layers that serve different purposes. The entire thing, when we put everything together, we're aiming at reconstructing each individual particle as it traverses the detector layers. We try to follow the path of the particle in each layer where it leaves a trace, and then combine this information to match deposits between the different subdetectors, and really get a global picture of the event where each reconstructed particle is determined by the subdetector that gives the best and most accurate information for energy measurement, momentum measurement, etc. So, of course, we've probed a dark sector and new particles heavily at the LHC. And this is a map of a paper that we just published beginning of the year from CMS that is sort of a review of what we've accomplished so far in the first 10, 15 years of CMS with regard to dark sector or physics beyond the standard model. You can loosely group this into, simplified dark sectors where there's literally, compared to the standard model, one extension, let's say a new force carrier, a new force particle, and a dark matter candidate particle, like a minimal extension to the standard model. And there are other theories that, feature more sophisticated scenarios of how new physics may manifest and how it may be realized in nature. Think about arbitrarily number of forces and interactions that can be very, very complex and have complicated dynamics, such as quantum chromodynamics in standard model just on the dark side. Or supersymmetry, right, is a prominent example. Now, we've mapped this entire search plane and a plane of possible BSM scenarios. And of course, we've looked for each and every one of them. And I can show you how this results, accumulating and summarizing 10, 15 years of CMS searches looks like. And each individual plot of this is basically a statement that we didn't observe anything that contradicts the standard model. And that's all we could do was basically to place upper limits on the parameters in the extended models, in the models beyond the standard model. Let's say, a new particle may still exist for supersymmetry, but then the mass of this new particle would have to be heavier than X, because otherwise we would have seen it at the LHC. A new particle that extends the standard model may exist, but then may still exist, but then the coupling of that new particle to the quarks or the proton constituents that we smash together at the LHC would have to be lower than X or Y. Otherwise, we would have seen it at the LHC. It would have been produced in abundant matter, and we haven't seen anything that is particularly striking. So that's kind of very disappointing. And since the evidence that there must be physics beyond the standard model is so convincing, we're still, thinking what could have gone wrong in our searches, and basically why haven't we observed any of these scenarios, right? So, and the big question that we're trying to ask and starting to ask, or have started to ask in the couple, 1, 2 last years, maybe we're looking just in the wrong spots for the wrong models. Maybe theorists haven't given us the right model yet, or pointed us to look for BSM in that way or in that topology. Maybe the right model wasn't in there yet. So maybe we should just reformulate the question that we're asking. And instead of asking the question, does a given collision event look like it's consistent with coming from supersymmetry, for instance? We should turn the question around and say, does this given collision event look like it's compatible with the standard model or not? And this is commonly referred to as anomaly detection. And the focus of the first part of this talk is how we do anomaly detection at CMS, looking for exotic or anomalous digit events, coming back to this initial event display that I showed you where it has 2 or 3 of these interesting jet objects. Well, first of all, what are the assumptions for anomaly detection? Actually, we don't want to make any assumptions, right? That's the point of it. We don't want to make any assumptions on how exotic or anomalous jets could look like. For instance, they could have long decay chains of new particles that decay into other resonances, maybe even standard model resonances like the top or the Z, that then decay into quarks. They could have completely exotic and weird particle and radiation patterns. I don't want to make any assumption in that regard. I want our algorithm to be as model independent as possible and not assume a specific signal model. The only assumption that I want to make is jets that are created from this BSM process, whatever it is, they should look different from the jets that are abundant at the LHC, which come from quark and gluon production, the so-called QCD jets, which constitute the main background at the LHC. There are 5 different analysis strategies that we have been pursuing over the last year. Don't worry, I don't want to highlight all 5 of them, but they all follow the same principle. Basically, you start from a pre-selected sample of dijet events that is cleaned against, detector noise, pretty sure, pretty plain vanilla dijet events. We train an anomaly detection algorithm that gives us an output that is a so-called anomaly metric, right? On which we can place a cut. And if we do everything right, and hopefully there is some new physics at a given resonance mass, remember the origin particle that decayed into the jets in the detector. If I do everything right, then hopefully once I place this cut, I can reduce the background significantly, the blue. By placing a selection, the background will be reduced significantly. While the signal, because the signal is anomalous and my machine learning algorithm has detected that's an anomalous event, and those are anomalous events, signal will be retained and suddenly will become apparent on top of a smoothly falling background. You will start to see a bump that comes from a new resonant particle decay. So these strategies that we're pursuing, they vary in model dependence. And the one that I am mostly concerned with and the most intuitive from my point of view is certainly the most model independent, which is the approach you learn how QCD jets look like, and then you look for outliers. And we're doing this with an autoencoder. Quick autoencoder fundamentals. Autoencoders are trained on non-anomalous examples, meaning on standard examples. In this case, bluefish swimming to the left. Well, in our case, it would be QCD jets, of which we have so many at the LHC that it's really trivial to compile a huge, gigantic set of QCD jet samples that we can be confident there's no signal in there. It's purely QCD jets. They fly around everywhere in the detector. And that's our bluefish swimming to the left that we train an autoencoder on. And this autoencoder will take examples of bluefish swimming to the left and try to feed their information, let's say, the color of the fish, the size of the fish, the size of the eye, into a neural network and force the information through a so-called bottleneck in the middle, and then outwards going, try to reconstruct the same fish again. And the point being is that by forcing the information through a bottleneck, you force the algorithm to discard irrelevant information or redundant information and really have it focus on the core features that make up a bluefish swimming to the left. And you can see the reconstruction quality if you compare the output image of the fish to the input. It's pretty accurate, right? Maybe the color is a bit off, but overall it's a very, very small reconstruction error. Similar here for this fish, well, the color is got a bit darker and got a bit bigger, but overall pretty good reconstruction. Now, the idea behind it is that once you're done training and then you let the algorithm run on a new data sample where suddenly you might think maybe there is some exotic multi-jet event in there. Maybe there is some redfish swimming to the right in the new sensitive signal sample. Well, if there is such a exotic fish in there, it will make a large error in reconstructing the fish, right? And suddenly the difference between the output image and the input image is pretty significant. And actually, if you then plot the reconstruction loss, you will find that the anomalies are concentrated on the right, whereas the bulk of the distribution is just, your average bluefish swimming to the right, your left, your average standard model QCD jet. And that's exactly the anomaly metric that you can then place a cut on and select a bucket of events that contains really only the most anomalous jets. That's the idea behind autoencoders. There is a second strategy that we're pursuing, which already has a bit more model dependence, but still pretty model agnostic, which is the idea to train a classifier between two samples with different signal purities. It's called weak supervision. It's illustrated a bit here. So suppose you have two buckets of events, and all you know and all you need to assume is that the interesting stuff, the anomalous stuff, has a higher concentration in one bucket than the other bucket. What you can do, even though without assuming what the anomalous events look like, you only need to assume that there's a difference in concentration between the two buckets. You can train the one bucket against the other bucket, and it can be shown that this, comes out as a classifier that can isolate and can pick up on this concentration difference and can learn what this anomaly in the one bucket of events looks like. And of course, the larger the gradient, the larger the concentration difference, the better the algorithm will be. There's actually sort of like a turn off or a turn on and like really a concentration difference beyond it really picks up then and learns to distinguish signal versus background. And this is a concept that we're employing in our research because, well, it all depends now on what you construct as the mixed sample one and the mixed sample two. And that's exactly where a little bit of model dependence comes in, unavoidably. You have to construct these mixed samples one and two. You can't just randomly sample your events and it would have exactly the same concentration, right? So assuming that your signal is a resonance in the MJJ spectrum, in the diejet invariant mass spectrum, below a smoothly falling background, well, your mixed sample two, your background enriched sample would be the sideband in the close vicinity, but not, in the close vicinity of a resonance, but not covering the resonance. And your mixed sample one would be the signal-enriched bucket of events straight on where you expect the resonance to be. And this expectation where the resonance you expect it to be, that's the model dependence that creeps in a bit. Finally, there is a third approach, of which I don't want to go into much detail, but it's called QUAC, quasi-anomalous knowledge, and you basically encode a prior of potential anomalies and then look for similar events in data. The thing to take away here is that 50% of this approach is identical to the autoencoder approach. You also, again, train an autoencoder on background like jets, on bluefish swimming to the left. But then you also train a second autoencoder on a simulated bucket of redfish swimming to the right, to stay in the example. And so basically you encode a prior in an additional autoencoder of how a signal could look like. Basically, throw all the different BSM scenarios together, SUSY, dark quantum chromodynamics, etc. You get a colorful mix of how BSM jets could look like, and you train an autoencoder on that. And then, well, if you construct a 2D plane between signal loss and background reconstruction loss. Your interesting events will be like at high background loss. So your background autoencoder says, I have never seen this type of event or jet. I don't know how to reconstruct it. And your signal loss is pretty small because your signal autoencoder says, I've seen these kinds of jets. I've seen them in the training. You've given me dark QCD jets, and they kind of look alike. I can reconstruct them pretty well. And that's the phase space in this two-dimensional plane that you want to select and place a quadratic or like a square anomaly metric cut on this corner of phase space and do your bump hunt finally in that region. So coming to this bump hunt, of course, we do everything first in Monte Carlo, right, to see how our algorithms perform, to demonstrate that they perform, in fact. So how this would look like, right? I take a very generic BSM model where there is a new particle X that decays into two new particles Y and Y prime resonances that they themselves decay into two quarks. So this is, each one gives rise to a two-pronged jet, which is very different from QCD because QCD, you would expect to have one prong. So two-prong jets, we should be able to flag as anomalous. And we quantify the performance on a simulated mock data set by injecting some of these events in a simulated background sample. Well, if we do that and we look at the digit invariant mass, by eye, no chance of seeing like a bump here where we injected the signal, right? It's completely smoothly falling. By eye, we wouldn't say that there is a BSM signal. But so let's see how this looks like once I place an anomaly metric cut. I think in this example, it's for one of the weakly supervised methods. So suddenly, if you train a weakly supervised classifier in the style that I showed you here, and you assume the right resonance mass at 3 TeV, suddenly you can see that your anomaly metric cut greatly reduced your background by 2 orders of magnitude while leaving the signal virtually untouched. It retained all the signal events. And suddenly you see this bump here, right? And if you quantify the significance of this bump, you basically go from 0 sigma to 7 sigma straight out of the box, which is Nobel Prize level, right? If this were real data, unfortunately, it's not, right? But just to quantify and measure the performance, the expected performance of our algorithm, and this 7 sigma you need to compare with 3 sigma significance from non-machine learning based traditional algorithms. So machine learning and anomaly detection with machine learning really in a completely model independent fashion helps you to surface rare events without assuming what the physics behind it is. Now, this is simulation. That's why there is this label. We also check before we go into looking into the real data, of course, the correlations between the different approaches. We have the autoencoder, we have weakly supervised methods, we have Quark, the third method that I presented. Overall, you can see that the complementary, well, the correlation scores between these are very, very small, surprisingly small for, two hypothetical BSM scenarios and for the standard model background, which really means they pick up on different parts of the jet, or if one algorithm misses out on an anomaly, another one would probably find it. That's why they're complementary. So, and now coming back to the event that I showed you at the beginning. I showed you this for a reason, because this event is from the entire run-to data taking period from CMS from the years 2016 to 2018, which has been the most successful and most used data set in the history of CMS. The autoencoder says this event is the most anomalous from looking for exotic digit events point of view. And it's not only because these have a combined invariant mass of 4.5 TeV. It's actually because the substructure of these jets is very non-QCD-like. I can tell you why. For instance, this jet here at the bottom has clearly several what we call prongs, right? These regions of high density There are several particles. Here's one prong, several particles going into this direction, several particles going into this direction, and there's maybe a third prong. Exotic thing about this jet is that these two prongs here, they're right at the edge of the cone, which is quite unusual. It's a very broad jet with prongs right at the edge of the cone, which is not something that you expect at all from QCD jets. And second here, this jet is very anomalous because the particles in this one prong, you might argue, okay, there's only one prong. It looks very QCD-like. But this one prong, the hierarchy of the particles that make up this one prong is very non-QCD-like. Typically in QCD jets, you have one particle in the middle of the jet that dominates everything, and then you have some subordinate particles around it. Here you have 4 or 5 particles that carry a tremendous amount of energy, almost on par with each other. And that's something that was detected by the autoencoder, and we looked at it and we were able to understand why it was flagged as highly anomalous. So this is the most anomalous event, and it would be great if this wasn't the only one that was flagged as highly anomalous. Especially maybe we observe 200 extra events all at the same digit invariant mass at 4.5 TeV or something, right? So that would be great. So now let's basically open the box and look at the whole data set in run 2 and look at the digit invariant mass of the most anomalous events. That's the spectrum after a cut on the autoencoder, with some overlaid to guide the eye how a signal would manifest at 3 TeV or 5 TeV respectively. Already by eye, and then also if we do it with our, if we quantify it with our significance metrics, etc., there is no significant axis observed in the entire spectrum, unfortunately. Also not with the other methods, weakly supervised or quark. Everything is unfortunately consistent with smoothly falling spectrum from the standard model. However, if there was a signal hiding, we demonstrate that we get a large improvement over an inclusive search strategy or a search strategy that's based on traditional and not machine learning based approaches. So basically, it's a messy plot that takes a long time to digest, but if you just focus on the bottom ratio, as soon as a point here, each point is a different of these strategies. That's autoencoder, weakly supervised, the quark method. As soon as a point is above this line, that is at 1, a dashed line at 1, as soon as we are above that, we gain compared to an inclusive strategy that doesn't use this machine learning based approaches. And as you can see, almost all of the times we gain through these approaches. And this is the first anomaly search for CMS with machine learning, and there are many, many more to come. This was really just basically the kickoff event. And maybe on this note, I want to quickly say what we want to do at CMS in parts. Right? There is much more than I could talk about, but what the next 10 years could look like. Well, I don't have to explain to you this plot because it's your plot. But just to say the volume of data at the LHC, especially at the high Lumi LHC in the next coming years, exceeds what's going in and out of Google Cloud, right, per second. It's a tremendous amount of data and too much to store, too much to process, too much to analyze in great detail every event. That's why we have a 2-tier triggering system in place, right? The first one is implemented on hardware FPGAs, reduces the event rate that happens at 40 megahertz where we collide the protons to something that is amounting to 750 kilohertz roughly. That will be the rate. And then there will be a second stage running on software or GPU, called high-level trigger that finally reduces the rate to something very manageable that we can store the full information off onto disk and take our time to analyze it in the greatest detail possible. But the point is, going from 40 megahertz to 1 kilohertz, basically it means that our triggers discard almost all the collisions, and we can only keep a tiny portion of the collisions that take place. Now, what does that mean? Well, there is a worst case scenario that we don't want to even think about, but we have to talk about. Typically, to first order, right, these triggers operate based on the energy of the event. We assume more energy, more interesting event, more worth saving, and the low energy stuff we discard, right? That's to first order how it goes. And that's as indicated here, there is a level 1 threshold that's pretty low or fairly low. And then, of course, the second trigger applies a higher threshold, and that's our final selected data. Now, what happens if new physics, what happens is if a new resonance that I talked to you about, like a 3 TV, a 4.5 TV, what happens if this resonance is not a 3 TV, but a 300 GeV or 30 GeV? Well, it's really as dramatic as it looks here. I have a siren here warning. It really could be that we're losing 100%, meaning all of our BSM events already at the trigger stage, at HLT or at the level 1, right? And this can absolutely not happen. We built the LHC for 10, 20 billion with the detectors, and we cannot afford this scenario, right? It's our duty to exploit the full LHC potential, and we cannot come and say, okay, we produce new physics, but then we discard it immediately again, right? Absolute no-go. So that means the cure for this is we need to make better decisions at level 1. Of course, again, I don't have to tell you, the data intensity that I already talked to you about asks for high throughput solutions, and the higher the throughput, the more inaccurate, or the less time you have, the more inaccurate your solutions will be. But the silver lining is that if you manage to somehow just, lower your thresholds or tweak your selection at the level 1 in such a way that you gain in terms of signal acceptance for a BSM scenario at the 20% level, at the end of the LHC lifetime, you will have a larger, a bucket of events that contains 20% more signal, and that equates to running the LHC 2 or 3 years, right? And longer than you would have to. And you can turn this into a dollar amount, and it's really impressive. So we absolutely want to get the help from AI in making these selections for anomalous events, for example. For that, of course, the models need to be put into FPGAs. The big problem there is you want to comply with the resource and latency budget that you have, which is very, very, very tight, right? And the elephant in the room, and there's a lot of research going into that. CMS, Atlas, Bell, they're all concerned with the same thing. How do I port the models that are so performant offline, because I can blow up their complexity and have built millions, well, when talking about JetGPT, billions of parameters, but let's stick with millions. How can I port such an algorithm on something as small and latency constrained as an FPGA? So a compression strategy is not a nice to have. It's an absolute must, right? And now coming to what CMS has started deploying as a, let's say, guinea pig as a first demonstrator in round 3, but this will, of course, be then taken way further in round 4, is anomaly detection in the level 1 trigger, something that we call axolitl. It's a variational autoencoder deployed on level 1 FPGAs. And of course, you can talking about this compression strategy, you can quantize it, etc. You have to, but you can play several tricks to quantize and compress your networks. Right? The trick of the axolotl autoencoder deployed at level 1 is simply that if you refresh your memory how variation autoencoders are trained, you have basically a reconstruction term in the loss that quantifies how accurate your blue fish swimming to the left, your output image, your output fish is to the input fish. But you also have a regularization term that basically penalizes if your latent space of basically the bottleneck of your autoencoder isn't well behaved, meaning if it doesn't look very Gaussian, you have several modes, how large your bottleneck is, and they should be kind of several Gaussians that loosely overlap, not too disjoint, not completely overlapping, so that the idea behind that is that if you want to use it and really understand it as a variational autoencoder, you can use it as a generative model and sample from this latent space. So you want to have a well-behaved latent space. But basically, this term can be used as an anomaly metric as well. It doesn't have to be this reconstruction term. Can also be the full regularization term. And for that, you only then, since it's happening all in the bottleneck, you don't have to evaluate the second half of your autoencoder anymore, your decoder part. Forget about it. It's enough to work with this KL divergence term. So by the end of the data taking of 24, we have already 10 terabytes of AXO-triggered data, for which we then write out almost the full event information. And here you can see how this looks like. Here's the anomaly score. Of course, the most anomalous, most of the events are not very anomalous, right? All your zero bias, min bias events, they have a very, very low anomaly score, and you're not interested in them. You're interested in the high stuff that has a high anomaly score, and you can define various trigger thresholds. Of course, if you select events at lower thresholds, you have a higher rate. At higher thresholds, you have a lower rate. That all needs to be coordinated within other activities of CMS in the trigger because they're all eventually competing for bandwidth. But this is deployed in 24, and the question, once we selected the data with these anomaly triggers on FPGAs, first question to ask is, can we find standard model candles in the data, right? Can this triggering algorithm and triggering paradigm see that, okay, compared to really, soft QCD collisions, almost non-diffractive, almost elastic or loosely inelastic, right? Compared to this min bias, zero bias. Can my algorithm see that this is already, if I produce a Z, that this is an exotic event, that a chase psi is an exotic event? And the answer is yes, we can. We can see these anomalies in the data, because really for us it's standard model according to the textbooks. They're in our textbooks, but compared to zero bias events, those are anomalies in the data, and it's a good test and validation of the concept. But what can we do ultimately with the events that the algorithm selects? Well, looking further into the kinds of events that our algorithm selects, and I think I have like 10 more minutes, so I should be good. Well, we tend to select events with high multiplicities of objects, a large number of jets, a large number of photon objects or electron objects, surprisingly a low number of muon objects. But also, what's really interesting and what's almost philosophical then, if you look at this is the full rate of events that we store in this trigger with this trigger path. If you look at the events that are what we call the pure rate, basically the events are not being selected by any other algorithm that we have in the trigger. We have triggers that select events with 2 muons. We have triggers that select events where there are 8 jets with a combined energy of 4 TeV. Of course, we have triggers to select these events. But looking at the events that are singularly triggered by the autoencoder, by the anomaly detection, and by no other trigger, we see that this is the pure rate. Events that have quite a low anomaly score, surprisingly, because, well, it makes kind of sense, because high anomaly score to first order again means higher energy, and these higher energy events would have already been selected by other triggers. So this is really the net gain that we have by these anomaly triggers. And then what can we do with these events? And this is, of course, now in progress. We can perform die-object bump hunts, kind of what I showed you, but not for standard model resonances, but for hypothetical new scenarios that would show up as a bump in dimuon mass, in dijet mass, whatever die-object combination you can think of. Again, here, similar plot that we show that we select with this anomaly trigger events that have pretty low missing transverse energy. Of course, we do also select events that have high missing transverse energy, but they are already triggered by other data streams and triggering algorithms. So the uniquely triggered events have low missing transverse energy. And hopefully that will be the coolest thing. Eventually we can, aside from, looking for resonances, looking for exotic signatures, we can release at the end of the run 3, for instance, sort of a catalog with all the most anomalous events triggered by the actual little anomaly detection trigger. And we can maybe identify, with the help of theorists, etc., clusters of events that would point to, there's my cluster of top quark events, there's my cluster of Z boson events, there's my cluster of QCD events, and then there is a cluster maybe that I cannot identify, and I have to understand, where do these events come from? That would be, of course, the killer plot to look at. It won't be as pretty in reality, but that would be the ideal goal. Okay, finally, for the last 7 or 8 minutes, I will talk about how we can push things further, going away from classical computing and classical approaches to basically tapping into quantum computing. So why do we want quantum algorithms, especially for anomaly detection, but for any other purpose, right? Certainly, and again, I mentioned this is not the next 10 years, this is maybe the next 100 years. Probably FCCHH, if I extrapolate the timelines, maybe, who knows, right? Quantum computing could be just today's machine learning and today's computing. So the future experiments, for sure, they will have even higher data rates than what we have today, faster inference requirements, and really these techniques that we're pushing so hard right now, eventually they could saturate. So we're very interested, I am personally very interested in even next generation computing paradigms, because they really could potentially unlock better representations of the data. When we talk about an algorithm, a machine learning algorithm, it's 80% of how good it will perform is how well does your algorithm match and is able to learn the data and its representation. Can we have powerful operations to manipulate data as well, or to filter through data very fast? And then, of course, we have quantum mechanical phenomena, right? Such as entanglement, superposition, tunneling, for which there are no classical equivalents, and which are entirely new paradigms. And they also have a significant parameter complexity advantage. So what you will see in a couple slides is that quantum algorithms can achieve similar results at way fewer parameters in terms of how complex your algorithm, or your circuit for that matter, is than classical solutions. Yeah, so entanglement could mean that I can uncover deeper patterns in data, or capture higher order correlations. There's superposition, right? Maybe that's a efficient representation of multidimensional data. That's why we're very interested in quantum algorithms. So brief, one slide, quantum computing basics. The building blocks of quantum circuits or quantum computers are qubits, where a classical bit is either 0 or 1. Of course, you may have already heard or learned or remember that a qubit is a superposition of a 0 state and a 1 state. So basically, when we think about quantum computers, it's typically a spin up or spin down of an electron, for instance. And I can map any state that is a superposition of spin 1 and spin up and spin down, superposition of 0 and 1 onto this Bloch sphere. And basically I can assign two angles, theta and phi, to this point on the Bloch sphere, and that defines where the qubit is. So when I want to build a quantum circuit, basically what I do is I manipulate qubits all day long, right? I have a system of states, and I manipulate the states through gates. I can rotate the states, right? for instance, rotate around these axes of the Bloch sphere, I can entangle two states together. So the recipe, or virtually all of the quantum circuits, are built in these 3, 4 steps. So to say, you first encode your data. So here's your input data, whatever data you want to encode on the quantum circuit. You encode it, then you entangle if you want to. You rotate, you can apply further gates, and finally you measure and get an observable out. So if you look at this, going from a plain quantum circuit to what makes a quantum circuit an element of quantum machine learning, is that simply these parts are trainable, right? You assign trainable parameters to how you want to encode the data, to how much around these axes you want to rotate, right? You can literally train parameters that describe I rotate by 40 degrees, by 60 degrees, etc. These are trainable parameters. And how much you want to entangle states. And that's how you go from a plain quantum circuit that stands on its own to a trainable circuit, which brings it into quantum machine learning. And if you look at this, so I told you, this is classical data that you shove onto the quantum circuit, you encode. So for instance, these would be 4 features that you encode. First through an Ry, Rx rotation, each feature. Then you entangle the first and the second qubits, the second and third and the fourth, and the fourth and the 0th. You rotate again, and then you measure, for instance, the first qubit. If you look at this closely, you will find a sort of analogy to a classical neural network. Let's say we're talking about jet tagging with graph neural networks, okay? The classical data would again be your 4 input features that characterize your jets, like 4 particles in the jet or something. Whatever you do, typically you will find that you first need to do an embedding, right? You basically turn your data, your input data, into a different space, right? Such as similar to turning classical data into a quantum circuit or encoding them onto qubits. Going into this embedding layer is a very similar concept, right? You just want to enter a different domain, a different space that can be trained and optimized. Then you have this middle part that entangles the different qubits, basically lets the information talk to each other. You have a further, you can add further rotations that have each one has a trainable parameter, for instance. But certainly this step most closely resembles a message passing step where basically a particle or a qubit here in the upper part, an element of the algorithm in the lower part starts to feel that there's stuff around it, right? Other nodes in the graph, in case of a graph neural network, other qubits in the system, in the case of a quantum circuit. So this is sort of the message passing part. And finally, you measure. In this case, it's measured onto one qubit is measured. And this is sort of equivalent to a global pool operation or just a softmax where you get one output node out. So there's a close analogy. And the problem now that I'm most interested in quantum machine learning is, especially coming from a high energy physics standpoint, where we always face the problem that our data in our detector, let's say we measure jet energy or a particle energy in our detector, that's a classical value, right? It's 80.5 GeV. If I measure another jet, it's another classical value. So basically, the big problem that we're facing in high energy physics is that our data, tabulated data that we're analyzing, isn't really a quantum mechanical system that I can easily map onto a quantum system. So far, most of the existing work for high energy physics on quantum circuits has focused on, okay, what do I do here? How do I entangle? How do I extract the most performance out of my circuit downstream in the circuit, to achieve whatever objective I want, jet tagging, anomaly detection, etc. And it always feeds in classical data, and there is some encoding step. Now, the big problem with this is that this encoding step, so far in existing literature, is very, very often, almost always basically, a black box, right? The question is again, how do I map my classical data when I measure energies in the detector onto qubits, and what does it mean, right? So many approaches in high energy physics and papers that have been published in the recent past. If I have here 4 qubits and I can basically come up with 4 features that I want to put on those qubits, often these are latent spaces, latent dimensions of an MVA. So basically, I train a separate autoencoder, for instance, beforehand, and with a bottleneck size of 4. And I say, okay, then once I've trained it, I can be sure that these 4 latent variables contain my full event picture, right? And then I push this full event picture onto the quantum circuit. But of course, as soon as you go there, your 4 dimensions are not interpretable anymore, right? You lose all the handles of any intuition. You have a latent space, then you go into a quantum circuit. It's just a black box on top of a black box, or a black box inside of a black box. And that's why this encoding step is something that interests me right now the most. And we've just published, or it has just been accepted in PRD, a paper that is introducing a concept that's called one particle, one qubit, or short 1P, 1Q, that really targets to make this encoding step, pushing my classical data onto qubits, as straightforward and interpretable as possible. And the idea behind it is we want to keep it simple. Instead of training an MVA beforehand and then using the latent space to push on the qubits, we say we represent one particle on one qubit. Each particle in our detector or in our jet gets its own qubit. Right? So I want to encode the kinematic features of the particle, the transverse momentum, and the eta, the pseudo rapidity, and the azimuthal angle in the detector, onto my Bloch sphere by using rotations. So one jet, if I talk about jet tagging or jet anomaly detection, would be characterized by n qubits. Of course, right now in my quantum systems, quantum hardware, simulation of quantum hardware, I cannot work with 100 qubits because I don't have the memory available. So I need to truncate basically the jet and say, okay, a jet is characterized by the 10 hardest particles in the jet. So one jet would be characterized by n qubits, 10 qubits, which stand for the 10 hardest particles. And this is a highly flexible encoding, as we found, and as I will show you, for anomaly detection, but also for supervised classification. It's purely quantum. There is no classical black box MVA in front that optimizes your or presumably optimizes, who knows, your latent space that you can then move on to the qubits. Is a straightforward one-to-one correspondence encoding. Details of the encoding, basically, you have, as I said, 2 angles that you can encode, theta and phi. On theta, we choose to encode, and we show that this is actually optimal, the pt times the eta of the particle, and for the phi, we choose the pt times the phi of the particle. And there is an additional trainable parameter that sort of, allows to scale the encoding during the encoding step and during the optimization of the circuit. And as you can see here, one example. So these are the 10 hardest particles on the Bloch sphere for a QCD jet in blue, and the red ones are the 10 hardest particles for one example top quark jet. And you see already by eye that the top quark jet sort of has a broader image. And this gets then further trained and optimized. So if we talk about anomaly detection with quantum algorithms, and I have 3 slides more. So, well, we want to compress the information into a bottleneck. It's not trivial in a quantum circuit because all these operations are unitary and they preserve inner products. So to actually destroy information is not trivial. It's not possible, actually. But there is a workaround that has been developed in the literature, which is basically by replacing some of the qubits that make up my input jet, for instance, by fresh 0 states, by reference qubits that I pull from the complete outside, that don't mean anything, that don't carry any information about my problem, and I just swap them out. And then I can artificially create a so-called bottleneck here by only, carrying through 2 of the qubits and destroying 4 qubits in this picture. So bottleneck size of 2. Um, and then I want to maximize my reconstruction quality, just like for the classical example where I want to maximize the reconstruction quality of the output fish image with respect to the input fish image. There's a subtlety here, which I don't want to, in interest of time, I don't want to go into detail. But the reconstruction quality is just the quantum fidelity between basically the output states and the input states. It's as simple as that. Okay, I will skip this and go to the results. So we trained our quantum autoencoder on the jets, where each jet is characterized by the Gen 10 leading jet constituents. Overall, it has about 30 trainable parameters. And then we performed a comparison to a classical autoencoder similar to what we're using in CMS, what I talked to you about in the first part of the talk. That has far more trainable parameters, 32,000. And as you can see here, the AUC, basically how well we can separate QCD jets from non-QCD jets, is across the board. We observe that our quantum autoencoder outperforms the classical equivalent. Same bottleneck size, quote unquote, etc., etc. And this is actually not only true for using simulated data, but we also checked how our autoencoder performs if we train it on real, actual CMS data for the first time. So quantum algorithm trained on CMS data for the first time. And you see here the quantum fidelity if you compare the simulated Delphis data set in orange to the actual data in CMS, which is 99% QCD, right? The response is identical, basically, and discriminates between standard model background and a potential signal like top quarks. So I will skip this. And the next steps are we can, now that we have this encoding that really maps one particle onto one qubit, we can look into how these algorithms learn and can we try to understand, for instance, jet substructure from how the qubits interact. So we're looking into things like quantum tomography, where really you can cook up something like resembles like an adjacency matrix or attention score matrix to see how particles react to changes in the circuit. So there are lots of things to understand. And we're also, maybe interesting for you, we're also investigating how not qubits, that's what you see here, behave, but Q modes, which is basically instead of using spin up and spin down electrons, which is a two-state system, continuous variable quantum systems like using photons, right? And the advantage of photons would be that they're super fast, right? Virtually speed of light inference time. They're super robust. It's very hard to interfere with them. So they would be ideally suited for like a on-edge setting at a next generation collider facility to process data and to analyze data in at the speed of light. Right? So there are exciting times ahead. And last slide is I asked ChatGPT to generate a Where's Waldo? High Energy Physics Conference setting to see if we can spot the anomaly. I think it got pretty nice, right? Here's Waldo. But I also said, look closely among the scientists to spot Waldo. So I think it's very obvious where he is. And fair to say that any of the algorithms I talked about today would have spotted this. So with this, I'm sorry if I ran a bit over time, but thank you very much.
Thank you, Benedikt. That was really good. That was very interesting, particularly the quantum stuff. We've been doing some thinking about quantum machine learning using for anomaly detection in real-time astronomy as well. And I think
Right.
it's again, I think you're finding what we're finding, that there is quantum advantage in that the number of parameters is far less and the results are easily comparable to sort of more complicated systems.
Yeah.
But the problem is really this encoding issue.
Yeah.
But yeah, no, that was great. Thank you. We have time for maybe one or two questions if anyone wants to ask anything of Benedikt.
Maybe I
Nope.
can ask one about the very early slide about the variation autoencoder.
Which one? Sorry.
So yeah, I think it's around slide 10 or so. It's mainly about because I'm wondering when you train the VAE, now you have this cut on your background spectrum, but you're still using bump hunting. How do you make sure the bump is not from bias of your
Right.
Anomaly score selection?
Yeah, that's a very good question. So exactly. So to let me see if I understood your question. Let's say if I place a cut here at 0.8 or something, right? Who tells me that this cut at 0.8 preserving, selecting the 20% or whatever, 5% most anomalous events here, that this cut doesn't introduce weird shapes in your background shape that create an artificial bump, right? That's your question.
Yeah, exactly.
So there's a thing that we do that I haven't talked about in the interest of time. You're exactly right. And this shows also up in the axolotl part that I talked about, where you see that the pure rate of, these basically high energies look very exotic to the autoencoder, right? So if you just naively go ahead and say, what are my most anomalous events? Those will be the ones that have the most stuff going on in the detector, the most energy. And if you then only select those, you will be biased towards high energies and you will maybe miss not as high anomaly score events at lower energies that are, but relatively speaking, just as anomalous, right? And that's why we do something that's called a quantile regression. Let's see where I have it. Here. Sorry. Right, so here's your two-dimensional score of, okay, those are background events. All the blue dots are background events. They have a certain MJJ, right? The density is higher here because it's QCD background and smoothly falling background, right? So the density is higher here and then gets very sparse, very few events at high MJJ values. And that's why if you train an autoencoder on these types of events or jets, the autoencoder, as I said, yeah, and as you said, will learn that high energy jets are more exotic because they are rarer in the training sample. And if you then place like this horizontal flat cut, suddenly your smoothly falling background shape will not be smooth anymore, but will actually have even the ability to climb and create artificial bumps or look very non-smoothly falling, and that's a big problem. And that's why we do this quantile regression, where we train an additional, once the autoencoder is trained and we construct this 2D plane, we train an additional small DNN, feed-forward MLP, that basically learns as a function of MJJ where you need to cut on this anomaly metric. This is the anomaly metric here of the event to retain the 1% most anomalous events as a function of MJJ, right? So, and this way, by a construction, if you then select only the 1% anomalous events with the strategy, your background will preserve the same shape and still be smoothly falling while your signal will still be a bump. That's how we do it.
I see. Yeah. Okay. This is pretty cool. Yeah, because we always also have the same issue when we do bump hunting. Also in Atlas, we have very similar issue before. So
yeah,
that's a very cool selection. Thanks.
Okay, great. Thanks again, Benedikt.
Thank you.
And yes, folks, look out for adverts for next month's A3D3 seminar. Otherwise, great. Thanks.
Thanks. Have a good week.
Yeah, you too.
Bye.
Everyone.